Welcome to my series of lectures on thermodynamics, and this is lecture number 11. In this particular lecture, I am going to discuss a topic which turns out to be pretty difficult to understand for most students and indeed causes confusions even among the experts. I am referring to the concept of reversibility. Exactly what qualifies a process as reversible or irreversible. In fact, we have already seen some examples of irreversible processes earlier. At least we have stated that certain processes cannot be run in reverse. Let me remind you that we talked of a situation like this. Here you have a cyclic engine working with only one reservoir, and at least the picture shows it absorbing heat Q and producing W. The work which is exactly equal to Q, because delta U here is 0. And of course, there is no other reservoir for heat to be rejected. Now this particular process is not really impossible. It is eminently possible if W is negative. In fact, as we have already said before, you don't even need a cyclic engine to achieve this. All you have to do is rub your hands together to generate heat, and you see an example of work being done on the system and being converted entirely into heat. So Q equal to W, that's always true. When this is negative, this is an eminently possible process, but this cannot be run in reverse. You cannot have a situation where an engine going in a cycle absorbs positive amount of heat from a reservoir and produces positive amount of work. We have also seen another example of a process which occurs all the time but which cannot be reversed. If you have an engine running between two reservoirs at temperatures T1 and T2, with T1 being greater than T2, then it's eminently possible for the engine to absorb an amount of heat Q1 from the hotter reservoir, reject an amount of heat Q2 given by minus Q1 to the lower reservoir, that is the colder reservoir, without doing any external amount of work or without having any work done on it. Indeed, once again, you don't really need a cyclic process for this to take place. All you need to do is put two reservoirs at different temperatures in thermal contact via maybe a conducting rod. Heat will flow from the hotter reservoir to the colder reservoir. But like the previous example, this one also cannot be run in reverse. You have no means of taking heat from a cold body and putting it into a hot body without any external work being done. So these are examples of two processes which occur in real life but cannot be run in reverse. Now why can't they be run in reverse? The answer to that is basically our experience. Of course, when you have a huge amount of evidence based on experience put together, and we have no further explanation for that beyond this kind of experience, we tend to make it a basic law. In fact, that's exactly what we do. As we will see later, this is exactly what the second law of thermodynamics is. Or rather, I should say, these two statements that we have made, that these two engines are irreversible, are two different but equivalent statements of the second law of thermodynamics. But right now, I'm getting ahead of myself. Before we can at all talk about the second law, what we should clarify is exactly what we mean by reversibility. What does it mean when we say that a certain process can be run in reverse, or, as in the case of these two instances, cannot be run in reverse? So we first need a proper definition of the term reversibility. Reversibility is defined in the following manner. A process carried out on a thermodynamic system is called reversible if, after it is completed, it is possible to return both the system and the surroundings to their respective initial states with no other effect. Now this is just a statement, but it actually hides a lot of nuance within it. So let us try to understand this by taking it apart into pieces. First, note that this is a statement about potentiality. It should be possible to return both the system and the surroundings to their initial state. It is not essential that you have to return them to their initial states. So it is enough that the process can be reversed. It does not have to be reversed for the system to be reversible. Now, what is very important is a system can always be returned back to its initial state. In fact, that happens in every engine, or rather, in every cyclic process. At the end of the cycle, the system is back in its initial state. That's exactly what a cyclic process means. However, a cyclic process may be reversible or may not be reversible. Because remember, for a process to be reversible, it is not enough for the system to be returned to its original state. The surroundings also have to be returned to its original initial state. And what is also important is this additional piece we have here, which may seem to be a bit of an overkill. After all, systems and surroundings are the only two things which interact with each other. So there should be no other effect if they are both back to their initial states. However, when we usually refer to surroundings in thermodynamics, we actually mean the things which interact with the system directly. Things far away which are not interacting with the system at the moment are not usually considered to be part of the surroundings. So it might very well happen that initially when a process takes place, the system may change state. Some other objects in its immediate surroundings may change state. And it should be possible to bring all of these things back to their original states, but at the expense of changing the state of something else which was not interacting in the first attempt when the system was actually undergoing the process. So, something which we did not really consider as part of the surroundings then. That is also not allowed. If a process is to be reversible, nothing has to change its state at the end of this reversal. Let me stress once again, you don't really have to carry out the reversal, but it should be possible to carry out the reversal in such a way that the system, the surroundings and everything else must come back to their original state. What we will do next is describe a reversible process, or rather, a nearly reversible process. Strictly speaking, an exactly reversible process does not really exist, at least with things that we can see around us. There are processes occurring in special systems like superconductors, which go very, very close to a reversible process. In fact, as far as we can tell with the experimental evidence at hand, these processes are reversible. However, most processes that occur around us are actually not really reversible. We are going to describe next a situation where we can get very, very close to a reversible process. In fact, as close to a reversible process as we want to. The system that we have chosen to provide an example of this nearly reversible process is a gas. Let's assume that it's an ideal gas. This is inside a cylinder with a movable piston. Now, there's something more that I've sort of tried to indicate in this drawing, which is, first of all, you have a tray on top of the cylinder which has a pile of sand. And on the side of the cylinder, there are tiny grooves which are sort of drawn inwards, so tiny that they will not cause any substantial effect when the piston moves here. In fact, we could have done this without the grooves. The grooves just make the description a bit simpler. And one thing that we have not indicated in this drawing is that the whole thing is actually submerged in a huge reservoir, maybe a huge water bath, and that's maintained at a constant temperature. And this wall is diathermal, so the gas inside is also maintained at a constant temperature because it's in thermal contact with the reservoir. Now what we do is, we take a tiny grain of sand from here, put it in a slot like this. Initially what happened was, the gas was in equilibrium because the pressure which the gas exerted on the bottom of this piston exactly balanced the force due to the pressure of the air or water from the outside, whatever was here, as well as the weight of the piston and the total combined weight of all these sand grains. So the force balance kept the piston in place. Now if I have moved, as I've said, a single grain of sand from here horizontally to a slot just to the side, I'm doing this horizontally so that no amount of work needs to be done in order to do this. Then what will happen is the force balance will be disturbed a bit by a very tiny amount. The pressure of the gas inside will be larger by a very tiny amount, so the piston will move up very slightly. Note that this movement is occurring so slowly that we can assume that the system is almost at equilibrium. At the next step, what I'm going to do is move another grain of sand, put it into a slot, maybe here. And the same thing repeats. The piston moves up very slightly. No work is done in the process in moving the sand grains. Of course, the gas does positive work when it goes up. And by this procedure, after I have moved substantial amount of sand away from this whole heap, it has been reduced to this. The gas has expanded substantially. And by the time I have ended almost all of the sand grains from the top of the tray here and stored them, as you can see, on these grooves on the side, the gas has expanded by quite a lot. Now, is this process reversible? The answer is, it is. All I have to do is to take the grains of sand back from these slots and put them back. Once again, I am doing that while maintaining the same horizontal level, so that no work has to be done for that part of the job. Of course, the gas now contracts because of this additional pressure exerted by the sand grains. Once again, this happens very slowly, and by the time we are back with the entire pile on top again, the gas is back to its original state. Note that the system is in contact with a heat reservoir, so its temperature did not change throughout, neither during the expansion nor during the contraction. At the end of the stage, the gas is back to its original volume. It was always at the same temperature as initially, so it's back to its original state. Now, has this really been a reversal? We have to be very careful when we make such a statement. Let's note that when we started, we had a pile of sand up here with empty slots. At the end of the process, of course, the pile of sand was emptied from the tray. They all landed up here. No work was done in moving the sand in this process. So, you don't have to worry about the agency which moved the sand. At least there was no energy exchange involved there. However, the gas did a lot of positive work when it expanded against the external pressure. And since the temperature has not changed, and this we are assuming is an ideal gas, its internal energy did not change either. So the positive work which it did must have come at the expense of heat flowing in via the diathermal wall from the outside. So by the time this process ended, not only did all the sand leave the tray and land up on the two edges, the reservoir also lost a lot of its energy and supplied it to the gas, which used it to do positive work. Now, has the process as we have described actually reverse that. Note that at the end, the pile of sand is back on the tray. All these slots are empty. And once again, this was done by moving the sand grains at a horizontal level. So the agency which did that took no part in energy exchange. No work was done in moving the grains of sand. And of course, now that the piston moved in, work was being done on the gas, or rather the gas was doing negative work on its surroundings. Once again, the internal energy did not change in the process, the temperature of the gas being constant, and what that meant was this work had to be dissipated away as heat. But the amount of work which the gas did when it expanded from here to here is exactly the same as the negative of the amount of work it did, or the amount of work which was actually done on it when it went from here back to here. So energy conservation would also tell you that that's exactly the same as the amount of heat it released to the reservoir. So reservoir 2 is back to its original state. Whatever energy it lost to the system while it was expanding, the system that is now given back to the reservoir when the gas contracts. So everything is back to their original state. So just to recapitulate, the gas is initially confined by the weight of the piston and sand and atmospheric or hydrostatic pressure, whatever is on top. As grains of sand are slowly moved from the tray to the grooves on the sides of the cylinder horizontally, the gas slowly expands. And to reverse the process, all we need to do is move the sand grains back to the tray from the grooves, once again moving them horizontally, so that the agency which does that does no work in the process. Now there's one important thing that we have to remember. This will work only if there is no friction. Now, exactly what would go wrong if there were friction? The argument here is slightly subtle. So let us talk about this carefully. Starting from the very beginning. For starters, if there were substantial friction between the piston and the cylinder walls, removing a single grain of salt or sand would not actually make the thing move forward. Friction would actually be enough to hold it back. Just to make our life simpler, let us assume that at the very beginning, the system is set up in such a way that friction is already at its limiting value. That is, it's just at the tipping point. Removing even one grain of sand is going to be enough to actually move the piston. I am going to ignore the small difference between kinetic and static friction here. That's really of no great consequence. But note that as we keep on removing the grains of sand, once again sideways to the respective horizontally placed slots, simply so that no work is done in that process, and the whole thing reaches its final point, now we have a problem. You have just put your final grains of sand here and here. Putting them back will not make the piston start moving down. Because now friction, instead of being downwards, will become upwards and halt the motion. Now the only way to overcome friction would be to add substantially more weight here, but we don't have anything else to add here at this point. But let's just assume that by some hindsight, we had stored some amount of sand at this height here. This doesn't really have to be sand, could be something else as well, could even be a single weight, which is just sufficient so that if we place this from here and bring the whole thing here, we will have enough weight for the thing to start moving down. After this, the thing starts proceeding in the same manner. You keep on adding more and more grains of sand and the thing comes down, and ultimately the whole thing settles down back at the same value. Note that at this stage, friction is actually upwards throughout, So when you are back at the same place, the pressure that the gas has to exert would have been less than the pressure you started out with, except that now you already have an additional weight that you have placed on your tray. So that actually causes the gas to have the same pressure at the final stage as the initial one. But in this whole process, friction did work throughout, or what is the same thing, to overcome the negative work which the friction did, you have to ensure that you have an additional weight which did more positive work. As a result, the amount of heat which the reservoir actually got back in its return journey was not the same as the amount of heat it get given. It actually has more now. And that's easy to understand. The weight which was up here has now come down here. That weight has done work on the system, and that ultimately has appeared as heat in the reservoir. Not as internal energy increase in the gas, because the gas, remember, is being maintained at a constant temperature and being an ideal gas. Its internal energy has not changed. So as the upshot of all this, what has really happened is a weight has come down and some extra heat has entered into the reservoir. So the system may be back at its initial state, but the surroundings are not. In particular, the weight which you had to use to force the thing down is actually not back at its original state. Of course, you could somehow lift it back, but the only way you can leave both the reservoir and this weight at their original states would be to convert the extra heat that the reservoir had received 100% into work and use that work to lift the weight back. Now, as you have already seen before, this thing cannot be done. Conversion of work into heat 100% is perfectly possible. It is reverse. The 100% conversion of heat back into work without any other effect simply cannot be done. Of course, this has to be without any other effect, because if you could achieve this with some other effect, and indeed you can do that, as we will explain later, it would still not be reversing the system and surroundings completely back to the original state, because now you would have something else which has changed the state. So, although in the frictionless case, this kind of quasi-static approach would have given you a reversible process, in the presence of friction, you do not have a reversible process out of this. So in general, in order to be reversible, we needed quasi-staticity but also the lack of friction. And this is actually a general statement. A process is reversible only if it is both quasi-static and dissipation free, which means that almost no natural spontaneous process can actually be exactly reversible. We can get very, very close to it, but exact reversibility is sort of an ideal idea for most daily life systems. As I have already mentioned before, there are systems like superconductors where you can actually achieve reversibility without any approximation, at least as far as we can tell by today's experimental standards. Now, as we have said, most real-life processes are irreversible. Let me now give you a few examples. Some of them you have met already. For example, the complete conversion of work into heat, which occurs, for instance, when we just rub our hands together, is an irreversible process. You cannot turn it around and convert heat completely back into work without any other effect. Another thing which happens all the time, transfer of heat from a higher temperature to a lower temperature without any other effect. This is also an irreversible process. These are the two processes that we talked about at the very beginning of today's lecture. And in fact, have talked about earlier also. You cannot have a process by which heat is taken from a colder body and transferred to a hotter body without external work being done or anything else changing on the outside. Now, these are not the only examples. You've met this one earlier as well. Consider a gas enclosed within an adiabatic wall into which you have inserted a propeller which you are turning through a current passing into the motor connected to it. Now, when the propeller churns, the pressure of the gas inside goes up. Now, this process cannot be reversed by turning the propeller in the opposite direction. To turn the propeller in the opposite direction, you have to apply torque, which is also in the opposite direction, and torque times the angular displacement will always be the same sign, and as a result, what will happen is the pressure will go up no matter whether you are churning the propeller clockwise or counterclockwise. This increase of pressure at constant volume, which happens by a process like this, is an irreversible process. You cannot actually reverse this and get everything back to where they were. Another very important example for both practical and even more theoretical reasons is the fact that free expansion of an ideal gas is irreversible. You cannot turn it back. Well, we will have a lot more to say about this particular example later, so let me just move on to the next one. The spread of aroma when a bottle of perfume is opened on one corner of a room is irreversible. By the way, let me just digress a bit and point out the fact that the aroma spreads so rapidly from one corner of the room to another is often wrongly attributed to diffusion, but diffusion is too slow a process to explain this. What is really responsible here is convection. Air streams moving around in the room carries the aroma from one end to another. Be that as it may, you cannot really expect that all the aroma will go back to the bottle once it's opened. You cannot reverse the process of the spread of the aroma. Another obvious example from daily life, you crack open an egg to make an omelette. Fine, that can be done. But this process is irreversible. The cracks don't seal and the contents of the egg does not return to the egg. So this is also an irreversible thing. In fact, you do see plenty of videos of eggs being cracked open and then suddenly reassembling themselves back, especially on social media. However, the moment you see such a video, you know that the latter half is being run in reverse. In fact, that's a sure shot sign that from our daily life experiences, we do know that certain things cannot really be reversed. There is something called the arrow of time, which tells us that certain things occur in only one direction and not in the other. So, irreversibility is something that we all actually know. We have to be a bit more careful when we say something is reversible. It is actually reversibility, which is really a rather alien situation, and we have to be very careful about understanding exactly what it means. Now, can we use any law to explain this irreversibility? Well, what about the first law of thermodynamics? Can it explain irreversibility? Well, as we have seen in previous lectures, the first law can be written as an equation. Q equals delta U plus W. Now, one property of an equation is the following. If A equals B, then minus A equals minus B. This means that if a process obeys the first law, so that Q, delta U and W for that obey the equation written here, its reverse, which will have heat minus Q, change in internal energy minus delta U, and work done by the system minus W, will also satisfy the same equation. So if a process obeys the first law, then so will its reverse. So the first law cannot explain irreversibility. In fact, nothing that can be expressed as an equation can say that a process is irreversible. The only thing that cannot really stay true if you change each side to negative of itself is really not an equation, but an inequality. If A is greater than B, then of course minus A is not greater than minus B. But at any rate, the first law will not do. We need a new law. But will only one new law do? After all, we saw many different examples of irreversibility above, and in fact there could be many more. Perhaps somewhat surprisingly, only one new law is sufficient to explain all of them. So all of these irreversibilities are actually at their heart just one irreversibility. If you could reverse or put in other words, if you could reverse any of these processes stated above, you could actually reverse all of them. The fact that any one of them cannot be reversed is actually equivalent to saying that all of them cannot be reversed. And this new law is what you call the second law of thermodynamics. Now the second law is going to dominate most of the topics that we discuss in the subsequent lectures. But before we go there, let me clarify one thing it definitely does not say. The first item that we discussed in my list of irreversible processes a while ago, as well as something we have been discussing for quite some time over past lectures, is the fact that the complete conversion of work into heat, when we rub our hands for example, is irreversible. What this does not say is that you cannot convert heat completely back into work. It just says that you cannot do this without any other effect. To illustrate what we mean by that, let me go back to our favorite example once again. The same gas, this time we have no friction between the piston and the cylinder, and we have this pile of sand on the piston's tray so that the gas is compressed down, and as we move the grains of sand slowly to a side, the piston slowly moves up and the gas expands. The gas of course does work in expanding, and since the internal energy of the gas does not change, remember this is still the same system, it's in contact with a thermal reservoir, heat has to flow in from the thermal reservoir in order to maintain the internal energy at a fixed value. So by the time the expansion has completed, what has happened is that heat has flown into the gas that did not increase its internal energy, and as a result, work has been done. The gas does work in expanding, and of course we know that because all the grains of sand that were in the tray have been now raised above the initial position. So heat has really been converted completely into work in this process. This does not run counter to the statement that we made that complete conversion of work into heat without any other effect is irreversible, simply because this has not occurred without any other effect. At the end of the day, this gas has expanded. Note that this is a reversible process, and we could of course bring the grains of sand all back and bring the piston down all the way to the position it was before. We have actually discussed this in great length a while ago. But if you did that, then at the end of the process, all the work that the gas had done on expanding would have been undone and the heat would have returned back to the reservoir. But as far as this portion of the process is concerned, the expansion of the gas alone, their heat is being converted completely into work, assuming of course that the gas is an ideal gas, so that since it's maintained at a constant temperature, it does not change its internal energy. But the important issue is that is not without any other effect. The gas has expanded. Now I will finish today's lecture discussing what I really meant when I said that all these irreversibilities are really the same irreversibility. Now, I cannot actually explain all of these here, that would take way too long. So I will just take one typical example. I said earlier that free expansion of a gas is irreversible. Let me explain why that irreversibility is exactly the same as the first one in our list, the one we have just discussed again. Complete conversion of heat into work. To see this, let's go back to our favorite system. Here we don't have any bunch of sand. On the tray, all the sand has already been placed here in these grooves. The tray is being held in place by a clamp. The clamp could be magnetically activated, for example, so that I could switch it off from outside. And let's say the pressure above is zero because it has been completely evacuated somehow. Now I release the clamp, and of course there's a huge imbalance of force on the two sides now. The gas inside is pressing onto the piston. There is no gas outside or nothing outside to press it back. So the piston suddenly shoots off and this expands quite a lot. Of course, there is some gas on this side which increases in pressure as its volume decreases. So ultimately this comes to an equilibrium somewhere. Now we are also assuming that the gas is ideal and the sudden expansion has not changed its temperature at all. Remember, the whole thing is in contact with the thermal reservoir, but the thermal reservoir would typically take some time to supply the necessary heat if any was needed, but Joule's experiment tells us that for an ideal gas at least, this process would require no flow of heat from the reservoir inside. Delta U is actually zero. Now, why is this process irreversible? Can't we get the piston back to its original position simply by pushing the thing back somehow? In fact, we can, because we have all these grains of sand already stored in position for that. As we keep on adding grains of sand by moving them horizontally once again onto the tray, the weight on top increases and the thing slowly comes down. Ultimately, once you add enough grains of sand, this piston will be back at exactly its original location and the gas would have been compressed. However, has this reversed the process? It has definitely reversed the change in the state of the system. But what about the surroundings? Note that initially when this expansion took place, the volume of the gas changed. Of course, the volume of the gas above it changed. The reservoir did not supply any heat here, and all these grains of sand were where they were. Now that we have reversed the whole process, at least apparently, we have reversed definitely the state of the gas inside, as well as whatever tenuous amount of gas was outside, that's also back at the same state. Note that we have not actually reversed everything. Things are not back here. Why? Well, earlier there were grains of sand in all these slots. Now some of these slots are empty. Those grains of sand have been added to the tray and they have done work in bringing the tray down. So negative work has been done by the gas. But the internal energy of the gas is still the same. Remember, it's in contact with a reservoir and being an ideal gas, its internal energy does not change. So the negative amount of work which had been done by that gas has to be compensated by a negative amount of heat flowing in from the reservoir, which essentially means that whatever work sand grains did on this tray and subsequently on the gas, that actually had to flow out, that energy had to flow out as heat into the reservoir. So at the end of this whole process, the gas is back to its initial state, but neither the sand grains nor the reservoir are back to their initial states. So we have not reversed the process completely. We have only made the gas undergo a cycle. But all is still not lost. We could, of course, have reversed the process if somehow we could manage to take the heat back from the reservoir and convert it back into work and help it to lift all these sand grains. But we have to do this, remember, without affecting anything else. Now that is exactly what our first irreversibility tells us that we cannot do. You can convert heat completely back into work, but you can do that only at the expense of changing the state of something else. You cannot do it without any other effect. So, the fact that you cannot reverse the free expansion here is due to the same reason as the one which makes complete conversion of work into heat an irreversible process. We can repeat the same line of argument for each of the cases. For some of them, the argument would be more involved, and we really don't want to spend all our time talking about these examples. So we will move on. But this is a very important issue to bear in mind. You do not really need a bunch of laws to explain the fact that all of these processes are irreversible. One and only one new law will do. And that, as we have been saying over and over again, is the second law of thermodynamics, which we will formally meet in the next lecture.